Okay, in this tutorial, we'll make a robot and start to study the motion of the robot. First, I'll make an assembly file. And now I start adding parts to the assembly. And then I will make holes to set up the wheels on the body of the robot. Now let's continue by adding the wheels. All wheels are similar, so I will just make one wheel, then we will multiply this part and use the same part file. I made these holes here to just make it easier to see when the wheel is turning. Now I will continue to multiply the wheels. You can basically multiply by copy and paste. I'm just going to use the copy option and then paste. You may see some errors, but it's okay. You can click OK and use Control V combination to multiply the parts. Now to move the wheels to the right place, I will use constraints, and I will use concentric constraint to put each wheel on the specified hole on the robot body. So now all wheels are connected, and I'm trying to make a ground so I can fix the robot wheels to a surface. I will use the touch align constraint to put the wheels on the ground. You can go back to the constraint and reverse the constraint so it moves back. I don't need this constraint actually, I just wanted to move the robot the way the wheel's touching the ground. So that's why I'm removing it. It's not necessary. We don't want to keep the robot on the ground. We will then use the contact for this. And then I will fix the ground so it doesn't move. Let's make the ground a little bit bigger so we have enough space for the robot to move around. Now that the assembly is finished, we can move on to the motion analysis. Go to application and click on the motion, and then I will make a new simulation. Here you see that the constraints from the assembly are being transferred actually to the motion analysis. You can deactivate them or activate them again, but make sure to check all of these constraints again in the joints, because sometimes the software reads the constraint but makes it in a different way than you need. So make sure you check the joints, or make the joints, don't import them from the assembly. But now I'm checking all of the joints, so make sure that the origin is on the center. The first motion body is the wheel, and the base is actually the chassis of the robot. I'm gonna do this for all the joint. Here you see there is a problem. The action body is the chassis, and then the base is the wheel. We need to switch that, because the base should be the chassis of the robot and the action should be the wheel. Okay, all joints are okay. Let's save the file. And then let's define the contact. I want contact between the wheels and the ground. Make sure that you turn on the friction, then select the bodies that you want to have contact between them. Now that the contacts are defined, you can actually click on each contact, and the software will show you in red the motion bodies that are working in that contact. So it's a good practice to um, have proper naming for your joints and contacts. The way it makes sense, when the number of parts are increasing, the assembly is going to be complicated. So it's good to rename them now. It's going to be more simple to deal with later. Now let's add torque to one of the wheels. Since we have defined joints, we can use the joints to add some scalar torque to them. I'm just going to add torque to one of the wheels. I only need action only. I will show what happens if you add action and reaction. So let's add this one. You see here the torque vector on the joint. It will follow the direction of the joint. That's why you don't need vector torque. But by adding action and reaction, you see it's going to be double-sided torque. So now we have torque on one of the wheels. Let's now make a solution and then solve this. I'm gonna have it for 5 seconds, and the rest of the options are good. But check the gravity vector just to make sure that gravity is correct. Now let's solve the problem. Now from the results we can play the simulation. Here you see that the torque is not even enough to turn the wheel. The simulation is going, but the wheel is not turning. I will try to increase the torque, but first you need to go back to the model. Let's increase the torque and run the simulation again. Now let's play the simulation. Yeah, it starts to move slowly. Alright, that's gone. Yeah, that's good enough. Let's see it again. Adding torque is enough for many simulations, but we have another option here. So let's deactivate the torque. Since we have defined joints, we can actually drive the joints without adding torque. So if we go to the joint, you have the drive tab here. This will turn the joint, this will rotate the joint, and you just need to specify the velocity. And you see the options here. I'm going to go through the options. This is very important because later on you can actually control each joint based on some commands that you write or you get from MATLAB or other softwares. But let's use polynomial. Here we don't need initial displacement. We're going to have a 3 RPM motor to drive this joint. And you can leave the acceleration and jerk as 0 to have a smooth rotation that starts from 3 RPM. Now let's see the results. Now you see that no matter how low is your RPM, it will turn in the direction you specify. So unlike the torque, you just specify the velocity of the RPM and it will start to turn. Now let's increase the RPM and see what happens. Now you see a very smooth movement because the wheel is turning slowly. It's not actually turning around the car. Let's increase the RPM. Just remember that no matter how much friction you have and what's happening in your assembly, the joint is going to be driven. Now you see we have a very smooth movement. It falls off. Yeah. So in this case, if something is locking your movement, the simulation is going to fail. So be careful with this type of driving the joint. Now by increasing it, you will see the same action as we had with increasing the torque. Because now we have enough speed to actually turn the car around. Now we can run some analysis on the simulation. The first one is going to be trace. This is a very useful one. You can't trace anything in the simulation. First I'm going to trace the chassis of this robot. You can see the traces appearing here. So if I go to the animation and check the trace and play the animation, you see it will trace the body of the robot. But a better option is to add a point somewhere that you want to trace. To do this, we'll add a marker to this point on the chassis. And then I go back and run the animation again. But before that, I need to go to the trace to remove the chassis and add this marker in the trace. I run it again and you see that the marker now is being traced. This is a good option because now I can change some other parameters like the friction, the torque acting on the wheel or anything else, and then trace it again to see the difference. So let's see the effect of changing the friction on the trace. Here by clicking on the joints and motion bodies, I can see which motion bodies have friction. I'm going to increase the friction a little bit and run the simulation again. If I run the animation again, tracing the new point is going to look like this. See, because the friction is more than before, the car is actually moving more. And the trace line is totally different. You can also use the plots like this. From the motion bodies, you select what you want to plot, and on the result view, you can select the plots and it will plot it for you. You can also see the plots while you are running the animation actually. So for example, let's see the velocity magnitude of the chassis of the robot. You see the velocity is increasing. That's actually where the robot is falling, because after a free fall, the velocity will increase. You can see it on the plot. Yeah, as it falls down, the velocity is moving up, and you can actually read how big is the velocity and other parameters if you need.